On a bright afternoon in April of 2024, in a modest conference room at the Lawrence Berkeley National Laboratory, a group of physicists prepared to say something they were not entirely sure they were allowed to say. The wording had been argued over for weeks. The slides had been rewritten and rewritten again. The numbers on those slides were small, a soft nudge, a whisper, a preference in the data of the sort that any careful cosmologist has learned not to trust too quickly. And yet the whisper, if it turned out to be real, would carry an unusually heavy cargo. It would mean that dark energy, the invisible thing making up roughly 7/10 of everything in the universe, is not what the textbooks have said it is for a quarter of a century. It would mean that the accepted ending of the cosmos, the long cold thinning that physicists have written about with the resigned steadiness of a person describing a distant winter, was never really the ending at all. It would mean that a story the field had considered settled had, quietly, gone unsettled again. The name of the collaboration was DESI, the Dark Energy Spectroscopic Instrument. More than 900 researchers from more than 70 institutions gathered under a single acronym for a single purpose. Their machine sits 5 hours south of Tucson, on a stony ridge in the Arizona desert, at just under 7,000 feet above the sea. There, bolted to the belly of the Nicholas U. Mail 4-meter telescope at Kitt Peak National Observatory, is a focal plane crowded with 5,000 tiny robotic arms. Each arm carries a fiber optic thread. Each thread aims itself at a single, specific point of light in the sky, and the arms move together, in unison, reconfiguring themselves in under 2 minutes to take aim at 5,000 new galaxies, and then 5,000 more, and then 5,000 more, night after night, season after season, until the sky itself has been sifted. By April of 2024, the DESI collaboration had 1 year of that sifting to show. 6 million galaxies and quasars, 11 billion years of cosmic history mapped as a three-dimensional structure of positions and distances and faint compressions in the distribution of matter. The map itself was a marvel, the largest of its kind ever produced, but the marvel was not the point. The point was what the map said when you compared it, gently, patiently, against the standard model of cosmology. At the microphone that April, the DESI co-spokesperson, Alexei Luthor-Harnett, of the University of California at Santa Cruz, described the finding with a careful excitement. Beside her, Seshadri Nadatha of the University of Portsmouth, co-chair of the collaboration's Galaxy and Quasar Clustering Working Group, walked through the numbers. Neither of them made the sort of announcement that shakes a room. This was not that kind of physics. This was the kind where you say, in effect, we have looked, and we have looked carefully, and the universe is not quite behaving the way we thought it should. The dark energy that fills the cosmos, that unseen pressure driving galaxies apart from one another, appears, in their data, to be weakening, not vanishing, not reversing, just, quietly, over the deep unfolding of time, growing a little less insistent than it used to be. That single sentence, if it holds, is enough to rewrite the last chapter of everything. Because for 25 years the accepted story of the universe's fate has rested on the opposite assumption. Dark energy, in the accepted story, is a constant. It does not weaken, it does not evolve. It is a fixed property of empty space itself, and because of it, the expansion of the cosmos will not only continue but accelerate, forever, without pause, without limit, until every galaxy beyond our own local group has drifted out past our horizon and gone dark, until the last stars have burned themselves down, until the universe becomes a thin, cold, featureless field in which almost nothing ever happens again. If dark energy is weakening, that ending is wrong. We do not yet know what the new ending is. We do not yet know if the finding will survive its own scrutiny. The statistical threshold physicists demand before they use the word discovery, 5 sigma, the vanishingly small probability of an accident, has not been crossed. The DESI team was careful about this at the microphone. They used the word hint. They used the word preference. They used the phrase on the cusp. And yet a year later, in March of 2025, when they returned with 3 years of survey data and nearly 15 million galaxies and quasars mapped, the whisper had grown. Not into a shout, into a firmer whisper. As Nadatha put it, the evidence is stronger now than it was. This is a documentary about that whisper, about the machine that captured it, and the galaxies it counted, and the men and women who built it, and the century of quiet astonishment that led up to the moment when a 5,000-armed robot on a mountain in Arizona began to suggest, gently, that the universe might not end the way we had learned to expect. It is a story about a fudge factor that a discomfited Einstein once wrote into his equations, then called his greatest blunder, then had returned to him by history in a form he could not have imagined. It is a story about how the field of cosmology came to be so confident, and how a single year's worth of data began, in the softest possible way, to test that confidence. Settle in. Let us begin. To understand what is being questioned, you have to understand what has been believed. And what has been believed for a quarter of a century now has a name that sounds like an inventory list rather than a cosmology. Lambda Cold Dark Matter. LCDM. 6 letters, 1 Greek and 5 English, that together describe the entire universe as physicists have understood it since the closing years of the 20th century. It is not a poetic name. It is not meant to be. It is the name of a bookkeeping system that turned out to work. The bookkeeping goes like this. If you take everything in the universe, every star and planet and moon and cloud of interstellar dust, every galaxy and cluster of galaxies, every neutrino streaming through your body as you read this, and you add up all of its mass and all of its energy, you get a total. 5% of that total is what you can see, or at least what is made of the same stuff you are. Ordinary matter, atoms, the material of chemistry and biology and stone. 27% of it is something else, a form of matter that does not shine, does not absorb light, does not interact with radiation in any way we have yet detected, and yet exerts gravity like anything else. This is cold, dark matter, the invisible scaffolding on which every galaxy hangs, and the remaining 68%, the overwhelming majority, nearly 7 of every 10 parts of everything there is dark energy, lambda. The Greek letter, borrowed from Einstein's equations, standing in for a property of empty space itself. 5% visible, 27% unseen but gravitating, 68% stranger still. Say those fractions slowly. Almost everything in the universe is a thing we cannot see, and most of that unseen almost everything is not even matter. It is a pressure, a tendency of vacuum to push outward, a number, lambda, whose value the standard model treats as fixed for all time. The bookkeeping works because when you plug those fractions into Einstein's equations of general relativity, and you let the universe run forward, the results agree with the sky. They agree with the temperature and pattern of the cosmic microwave background, the leftover glow of the first light, which came free of matter about 380,000 years after the beginning and has been streaming through space ever since. They agree with the way galaxies are distributed across the visible cosmos, clustered along filaments and gathered around voids in a great foamy web. They agree with the redshift distance relationship of Edwin Hubble and Georges Lemaître, the finding that the farther a galaxy sits from us, the faster it is fleeing. They agree with the observed brightnesses of exploding stars used as measuring rods across billions of light years. They agree, and they keep agreeing, and for 25 years the agreement has widened and deepened until it became difficult to imagine the model being wrong. That is what a paradigm feels like from inside. Not certainty exactly, confidence, the sense that further measurements will refine the fractions rather than overturn the picture. And the picture the fractions paint is a picture with an ending. If dark energy is a true constant, a property of the vacuum that does not weaken and does not tire, then it will keep pushing forever. The expansion of the universe will continue to accelerate. Galaxies now visible to our telescopes will, over billions of years, recede from us faster than light can bridge the gap between them and us, and one by one they will fall out of view. Our own local group, the Milky Way, Andromeda, and their retinue of small companions, will remain bound together by their mutual gravity, and will eventually merge into a single vast elliptical soup of stars. But everything beyond will vanish. The sky will darken. The distances between the surviving structures and the rest of creation will grow past the horizon of causality. The observable universe will shrink to a single lonely island, and then the stars will begin to go out. Star formation, in the accepted picture, is projected to essentially cease around 10 to the 14th power years from now. 100 trillion years, a number so much larger than the current age of the cosmos that saying it aloud does not help. Let me try to give you a feel for it. The universe as we know it, from the initial hot dense state until today, is about 14 billion years old. 100 trillion years is roughly 7,000 of those. 7,000 times the entire history of everything that has ever happened, and only then does the last star finish forming. And after that, the long dark begins in earnest. Existing stars burn through their fuel. Small red dwarfs, the misers of the stellar population, hold out longest, sipping their hydrogen for trillions of years. But they too eventually cool. Neutron stars and white dwarfs radiate away their heat. Black holes remain for a while as the last remaining engines of anything resembling activity, and even they slowly evaporate through the faint quantum leakage of Hawking radiation, over timescales so absurd that scientific notation is the only humane way to write them down. At the end of all of this, if the standard model is right, there is a universe. But it is a universe in name only. It is cold beyond the meaning of the word cold. It is dark beyond the meaning of the word dark. It is thin, so thin that particles of matter, if any remain, sit separated from their nearest neighbour by distances that dwarf the observable cosmos of today. Nothing happens. Nothing can happen. Entropy has reached its ceiling. Time in any useful sense has stopped, not because the clock has broken, but because there is no longer anything for the clock to measure. Physicists call this the Big Freeze, sometimes the heat death. Both names try to describe the same silence. It is not violent, it is not cataclysmic, it is the opposite of both. It is the universe running out of the ability to be anything at all. Sit with that for a moment. That was the accepted end, not because anyone wanted it. Not because it made for a comforting bedtime story, but because it was where the mathematics led, given the fractions we had measured and the constant we had assumed. A cosmos that would go on, thinning as it went, until the going on itself became indistinguishable from having stopped. And it is this ending, this long, cold, mathematically clean ending, that the whisper from Kit Peak has begun to tug at. To feel the strangeness of the whisper, you have to understand something else about lambda, about that number sitting at the heart of the accepted model, the one that carries the whole story of the ending on its back. Lambda was not discovered. Lambda was invented. And it was invented by a man who almost immediately regretted having done so. Rewind then, more than 100 years, to Berlin in 1917. Albert Einstein was, at that moment, the most celebrated theoretical physicist alive. He had, less than 2 years before, completed the general theory of relativity, the work that recast gravity not as a force pulling on distant bodies, but as the curvature of space-time itself. The equations were beautiful, and more than beautiful, they were universal. They did not apply only to the falling of apples or the orbits of planets. They applied to everything, and that universality carried a consequence Einstein had not quite bargained for. When you took his field equations and you applied them not to a solar system but to the cosmos as a whole, the equations refused to sit still. They wanted the universe to move, to expand outward or to collapse inward, but not simply to sit there being the universe. A static cosmos, the kind of steady, unchanging cathedral of stars that nearly every astronomer of the era believed in, was not a natural solution to Einstein's equations. It was, in the mathematical sense, unstable, a knife balanced on its edge. This bothered him. It bothered him because there was, at the time, no observational evidence that the universe was doing anything at all. The nebulae, those faint patches of light strewn across the night sky, were still generally thought to be clouds of gas within our own Milky Way. The idea that they might be entire other galaxies, receding at enormous speeds, would not be secured until Edwin Hubble's work in the following decade. In 1917, from where Einstein sat, the sky looked eternal, and so he did what any physicist of taste might do when confronted with a set of equations that refused to describe the world he saw. He added a term. He called it lambda, the cosmological constant. A small extra piece slid into his field equations, tuned precisely to counter the tendency of gravity to collapse the cosmos in on itself. With lambda in place, the equations could produce a static universe, balanced, eternal, the kind of cosmos an early 20th century mind could rest in. He did not like doing it. In his own words, the term was theoretically unsatisfactory. Elsewhere, he described the situation the equations had created without lambda as senseless, as irritating. This was, in other words, not a discovery. It was a workaround, a tuning knob, a fudge factor added because Einstein could not, at that moment in history, imagine the universe being anything other than still. And then history moved. In 1923, at the Mount Wilson Observatory in California, Edwin Hubble identified a particular kind of pulsing star, Cepheid variable, in what was then called the Andromeda Nebula. Cepheids have a useful property. The pattern of their brightening and dimming lets you calculate how bright they truly are, which lets you calculate how far away they must be. Hubble's calculation put the Andromeda Nebula at around 900,000 light-years, a distance so much greater than anyone had previously assigned to a nebula that it settled a decades-long debate in a single stroke. Andromeda was not a cloud inside the Milky Way. It was a separate island of stars, an entire galaxy of its own, unimaginably distant. 6 years later, in 1929, Hubble published the paper that would change the shape of cosmology. Working with the spectra of dozens of galaxies, he showed that the light from them was almost universally shifted toward the red end of the spectrum, and that the shift was larger for the galaxies that were more distant. Redshift, in the language of relativity, means recession. The galaxies were fleeing, and the farther away they were, the faster they were fleeing. The universe was not still. The universe was expanding. Einstein's equations without lambda had been trying to tell him this all along. When the news reached him, the reaction, over the following years, was one of unmistakable regret. He removed the cosmological constant from his equations. He called it, in correspondence, no longer necessary. Decades later, he would describe it, in a letter to the Belgian priest and cosmologist Georges Lemaitre, as very ugly. And in an anecdote that has become part of the folklore of physics, recounted publicly in the 1950s by the physicist George Gamow, though disputed in its exact wording by later historians, Einstein is said to have called lambda the biggest blunder of his life. The scholar Mario Livio, among others, has raised the reasonable question of whether Einstein used those precise words or whether Gamow, warming to a story, sharpened them. Accounts differ. What is not disputed is the underlying sentiment. Einstein regretted having introduced the term. He wished he had trusted his equations. He wished he had let the universe move. There is something almost tender in that regret. A man of extraordinary mathematical intuition, confronted with a cosmos he could not quite bring himself to believe in, added a small term to keep the sky the way he remembered it. And when the sky turned out to be moving after all, he took the term back out and treated it as a mistake. For most of the 20th century, that was the story. Lambda was a footnote, a cautionary tale about not over-trusting your own aesthetic preferences when the equations know more than you do. Cosmology textbooks acknowledged it, sometimes with a smile. Working physicists did not use it. It sat for decades in a kind of quiet retirement. And then, in 1998, two independent teams of astronomers looking at very distant exploding stars discovered something no one had been expecting. The expansion of the universe, they found, was not slowing down under the weight of gravity, as everyone had assumed it must be. It was speeding up. Something was pushing. What they needed to describe that pushing was a repulsive term in the field equations of general relativity, a term that would resist gravity across cosmic distances, a term that would drive the expansion faster and faster. A term, in fact, that looked almost exactly like the one Einstein had put into his equations in 1917, and then, in shame, removed. And so, more than 7 decades after its author had disowned it, lambda came back. Not as a fudge factor this time, as a description of something real, or at least something whose effects were real, whatever its ultimate nature turned out to be. The mistake had been undone by the sky itself. Stop and feel the shape of that irony. A term invented to force the universe to be still is now the primary mathematical tool physicists use to describe a universe that is expanding at an accelerating rate. A blunder became a foundation. A discarded piece of Einstein's arithmetic became 68% of everything. And now, in the softest possible way, on a mountain in Arizona, a machine with 5,000 robotic fingers has begun to whisper that even this resurrected term, this reinstated blunder-turned cornerstone, may not be quite the constant we thought. If lambda is not a constant, then Einstein's greatest blunder is neither a blunder nor a gift in the simple senses those words suggest. It is something stranger, a term that was wrong when he invented it for one reason, and wrong when he abandoned it for another, and only partially right when the field brought it back at the end of the 20th century. A term whose full meaning may still be waiting for us on the other side of a measurement that is only now beginning to come in. The whisper from Kitt Peak has not settled anything. It has, if anything, unsettled a great deal. And to understand how that unsettling matters, how the difference between a constant lambda and a weakening lambda can rearrange the entire fate of the cosmos, we have to go back to the moment when lambda was returned to us, to the two teams of astronomers and their photographs of distant supernovae, to the runaway universe of 1998, To understand what those astronomers found, you first have to understand what they thought they were doing. They were not, in their own minds, looking for a new force. They were not looking to overturn anything. They were, in the plainest possible terms, trying to weigh the universe. They wanted to know how heavy it was. They wanted to know, in particular, how much matter it contained, because the amount of matter would decide the shape of its future. A universe heavy enough would eventually pull itself back together in a slow, inexorable collapse. A universe just light enough would expand forever, thinning toward nothing. A universe on the knife edge between those two possibilities would coast, slowing but never quite stopping. That was the question. How much stuff is there? How much does the universe weigh? Nothing more exotic than that. The way to answer such a question, in the middle of the 1990s, was to measure the expansion of the universe at two different times in its history, one nearby, one very far away, and to compare them. If the faraway rate was much faster than the nearby rate, the universe had been slowing dramatically and it was heavy. If the two rates were nearly the same, it was lighter and it was coasting. Nobody in the whole of the scientific community seriously entertained the possibility that the faraway rate might be slower than the nearby rate. That would mean the expansion was accelerating. That would mean something in the equations had gone badly wrong, or something in the universe had been left out. It was not on the menu. It was not what anyone ordered. To make the comparison, the astronomers needed a candle, a source of light whose true brightness they already knew. If you know how bright a candle really is, and you see how bright it appears from where you stand, the difference tells you how far away it is. A candle at the far end of a long hall is dimmer than a candle at your hand, and the dimming follows a very precise mathematical rule. Astronomers call such an object a standard candle, and finding good ones has always been one of the quiet, essential labours of the science. Without them, distances in the sky are guesses. With them, distances become measurements. The standard candle these teams chose was a particular kind of stellar explosion called a Type Ia supernova. The physics behind it has a certain terrible elegance. Somewhere in a distant galaxy, a white dwarf, the collapsed, exhausted core of a star that has run out of fuel, sits in orbit with a companion. Slowly, over enormous stretches of time, it pulls matter from that companion onto itself. It grows heavier, it grows denser, and when its mass approaches a very particular threshold, a value first calculated in the early 20th century by a young Indian physicist named Subrahmanyan Chandrasekhar, and which now bears his name, the star can no longer hold itself up against its own gravity. It ignites. In a matter of seconds, it releases more energy than the sun will produce in its entire lifetime. For a few weeks, it can outshine the galaxy that contains it. The beautiful thing, from the astronomer's point of view, is that this all happens at very nearly the same mass, every time. Different white dwarfs, in different galaxies, at different points in the history of the universe, arrive at the same threshold and detonate with very nearly the same energy. The intrinsic brightness of a Type Ia supernova is, to a good approximation, a property of physics itself. If you can find one, and if you can be sure it is the right kind, you have in effect a candle whose true brightness you already know. A candle billions of light years away, burning with a light you can compare to the light of a candle at your feet. That was the idea. In practice, it was much harder. Type Ia supernovae are rare. In any given galaxy, they occur perhaps once every few centuries. You cannot go outside and wait for one. You have to survey enormous stretches of sky, over and over, comparing images taken weeks apart, watching for the single pinprick of light that was not there before. You have to catch the supernova early enough to measure its rise to peak brightness. You have to secure follow-up observations on some of the largest telescopes in the world, on nights that were scheduled months in advance, without knowing whether there would be anything to observe. You have to distinguish, in the light of your candle, the small differences in intrinsic brightness that even Type Ia supernovae still carry, and correct for them. You have to be sure the dust in the intervening galaxies is not making the light look dimmer than it really is. You have to be sure the light is not being reddened, or scattered, or gravitationally deflected on its way to your camera. Every step in the chain is a place where the measurement could go wrong. Every step is a place where a careful astronomer will lie awake at 3 a.m, wondering. There were two teams doing this work in the middle of the 1990s. One had begun earlier, at the Lawrence Berkeley National Laboratory in California, the same institution that would decades later midwife DESI. It had been founded in 1988 under the leadership of a young physicist named Saul Perlmutter, and it called itself the Supernova Cosmology Project. For most of its early years it had struggled. The techniques it needed did not quite exist yet. The cameras were not sensitive enough. The computers were not fast enough. The idea of finding supernovae on demand, of scheduling telescope time in advance and reliably delivering a discovery at the appointed hour, was, for a long time, viewed by senior astronomers with something between skepticism and amusement. It could not be done. And then, gradually, as the detectors improved and the software matured, it could be done. By the middle of the decade, the Berkeley team was finding supernovae at a rate no one had matched before, and beginning to plot them on the diagram that would decide the weight of the cosmos. The other team was younger, formed in 1994 and international from the beginning. Its co-founders were an Australian-based American named Brian Schmidt, working out of the Mount Stromlo Observatory in the hills above Canberra, and a young researcher at the University of California, Berkeley, named Adam Rees. They called themselves the High Z Supernova Search Team, the Z referring to redshift, the astronomers' shorthand for how much the light of a distant object has been stretched by the expansion of the universe as it travelled. High Z meant far away. Highs meant looking back deep in time. The team was, in a sense, a response to the Berkeley project. Some of its members had come out of the same intellectual tradition and knew the same techniques. They were determined to do the work independently, with their own choices of instrument and pipeline and calibration, so that whatever answer the sky returned would be checked by two hands, not one. There was, between the two teams, the kind of competition that anyone who has worked at the edge of a scientific field will recognize. Not hostile, not personal, but sharp. Each knew what the other was doing. Each knew that a definitive result was going to appear in the literature soon, and that the credit for it would attach itself with permanence to the group that got there first, and honestly. They exchanged data at conferences with a certain guardedness. They pursued their reductions in private. They worked long nights on mountaintops in Chile and Arizona and Hawaii and Australia. Cold hands on the controls of instruments they had helped to build, waiting for the light of a dying star that had travelled for most of the age of the universe to arrive at their cameras. Here is what they expected to find. They expected the distant supernova, the ones whose light had left them billions of years ago, to appear brighter than the simplest picture would suggest. A universe slowing under its own gravity would mean that in the distant past the expansion rate had been faster, which would mean the light from those far supernovae had a slightly shorter distance to travel than a naive extrapolation would predict. Shorter distance, brighter light. That was the prediction. The question was only how much brighter. A lot brighter would mean a heavy universe, destined to collapse. A little brighter would mean a lighter universe, destined to expand forever. Somewhere in the middle would mean the knife-edge case. Those were the choices. Those were the possibilities anyone had bothered to consider. The supernovae came in dimmer than expected. Not brighter, dimmer. At first, in both teams, the response was not excitement. The response was a very specific kind of dread. The response of an experimentalist who has spent years perfecting a measurement and now sees, in the reduced data, a result that violates the most basic prior of the field. When your instrument tells you something impossible, the first thing you assume is that your instrument is wrong. You do not, at 3 a.m. in a mountaintop control room, sit back and marvel at your revolutionary discovery. You start looking for the mistake. You check the calibration files. You check the pipeline. You check the reference stars in the field. You check whether some cluster of intervening dust in a foreground galaxy might be reddening the light. You check whether the supernova you have selected might belong to a subtly different population than the nearby ones you have been comparing them to. Perhaps because the early universe made stars from slightly different material, and slightly different stars might produce slightly different explosions. You look, in short, for every reasonable thing that could be dimming the light of a distant supernova that had nothing to do with the geometry of the cosmos. Members of both teams have spoken, in the years since, about this period of doubt, about sitting with the plots on their screens and not quite believing them, about running the analysis again, about the odd unwillingness to tell colleagues, about the private conviction, held for weeks in some cases and months in others, that they must have gotten something wrong and simply not yet found it. That is what integrity looks like from the inside, not certainty. Doubt, carried honestly, until the doubt itself runs out of places to hide. By the end of 1997, both teams had made the same journey. They had checked and rechecked and re-rechecked. The dimming was not going away. The distant supernovae were, honestly and stubbornly, farther away than they should have been. The universe had not been slowing down for the past several billion years, it had been speeding up. Something spread through all of space was pushing. Saul Perlmutter first presented the Supernova Cosmology Project's evidence in public on the 8th of January 1998 at a press conference during the winter meeting of the American Astronomical Society in Washington, D.C. It was not, in that room, a shout. It was a physicist walking through his plots and stating what they showed. The mass density of the universe, measured this way, appeared to be smaller than the simplest model demanded, and, more troublingly, the geometry appeared to require an additional term. A term, he acknowledged, that looked very much like the cosmological constant. Within months, the High Z team published their own paper, led by Adam Rees, laying out an independent case for the same conclusion from a different set of supernovae, analysed with different code by different hands. The title of that paper, published in May of 1998, has since become one of the load-bearing citations of modern cosmology. It named, in a single phrase, both the observation and the framework, observational evidence from supernovae for an accelerating universe and a cosmological constant. The two teams had arrived at the same shore from two different oceans. That congruence, more than any single measurement, is what forced the field to accept the finding. One team could be wrong. Two teams, using different techniques on different supernovae with different pipelines, arriving at the same violation of prior expectation, that was much harder to dismiss. The journal Science, at the end of that year, named the discovery its breakthrough of 1998. 13 years later, in 2011, the Nobel Committee awarded the prize in physics to Perlmutter, to Schmidt, and to Rees, for showing that the expansion of the universe was accelerating. Half of the prize went to Perlmutter for the Supernova Cosmology Project. A quarter each went to Schmidt and to Rees for the High Z team. Say those names slowly. They are the names attached, now permanently, to the moment the fate of the universe was rewritten. Rest with that for a moment. A small number of astronomers, working with photographs of exploding stars in distant galaxies, changed the accepted future of everything. Not by proposing a theory, not by writing an equation on a chalkboard, by measuring carefully the brightness of light that had travelled for most of the history of the cosmos to reach their cameras, and by refusing to look away when that light came in dimmer than the textbook said it should. The whole revised story of the universe, the acceleration, the resurrected lambda, the 68%, the predicted heat death, flows downstream of that stubborn refusal. But naming the observation was one thing. Naming what caused it was another. The dimming was real. The acceleration was real. What was doing the accelerating was not. Nobody had seen it. Nobody had measured it directly. Nobody had a picture or a spectrum or a laboratory sample. There was only the geometry, the shape the equations demanded to fit the data, and the empty word for whatever it was that was making the geometry come out that way. That was where a theorist in Chicago came in. Michael Turner, of the University of Chicago, had spent the 1980s and 1990s working at the intersection of particle physics and cosmology, the field sometimes called cosmological particle physics, or just, more affectionately, inner space, outer space. He had a particular gift, colleagues have said, for finding the phrase that made a difficult idea portable. He was one of the first theorists to argue, in the years leading up to 1998, that the universe might contain a non-zero cosmological constant, on the grounds that other measurements, of galaxy clustering, of the ages of the oldest stars, of the cosmic microwave background, were pointing that way even before the supernovae came in. When the supernova result arrived, he was ready. The name he chose for the thing was, in retrospect, a small piece of genius. Dark energy. 2 syllables, ordinary words, a deliberate echo of dark matter, the invisible stuff whose presence had been inferred from the rotation of galaxies since the 1930s. The pairing was intentional. Dark matter clumps under gravity and helps to build structure. Dark energy, whatever it was, appeared to do the opposite, to spread through space uniformly and to push things apart. Turner used the term in a paper he co-authored that year with Drake and Hutterer in Physical Review D, and in a talk at a symposium in Australia, and it appeared around the same time in a conference article by the physicist Lawrence Krauss. Within a year or two, the phrase was everywhere. It was in the popular press, it was in undergraduate textbooks, it was in the titles of grant proposals. A field that had, for a decade, been chasing a nameless anomaly, now had a name for the thing it was chasing. Naming a thing does not explain it. Everyone in the field understood this. The word dark energy did not tell you what dark energy was. It was a placeholder, a convenient bag into which the community could put its ignorance until it had the tools to look inside. And in the first years of the new century, a great many theorists set about trying to peer inside that bag. The simplest possibility, the one that emerged more or less immediately, was the one Einstein had reached for in 1917. The cosmological constant lambda, treated as a fixed property of space itself, an energy density that did not thin out as the universe expanded because it belonged to the vacuum. Empty space, on this picture, was not really empty. It had a small, constant energy of its own, everywhere, at every moment. That energy exerted a repulsive pressure, in the language of general relativity, and that pressure drove the expansion faster and faster. It was the same term Einstein had written down and then withdrawn. It was the least imaginative option, and it fit the data. But it was not the only option, and the community did not converge on it immediately. Throughout the late 1990s and into the 2000s, theorists proposed alternatives. The most influential class of these alternatives went under the name of quintessence, a word borrowed, half in jest and half in earnest, from the ancient Greek notion of a fifth element beyond earth, water, air, and fire. Quintessence models proposed that dark energy was not a constant of space, but a field, a scalar field, in the technical vocabulary, that permeated the cosmos and whose energy density could evolve slowly over time. In these pictures, dark energy had once been stronger or weaker than it is today. It might grow stronger in the future, it might fade away. It was, in a word, dynamical. The mathematics of such fields had been laid out well before the acceleration was discovered. A foundational paper appeared in 1988, 10 years before the supernova result, by Bharat Ratra and P.J.E. Peebles of Princeton. Its title, unassuming, described the cosmological consequences of a rolling homogeneous scalar field. It described in detail what happened if space were filled with such a field, and if that field slowly evolved. At the time, it was a theoretical exercise, one of many in a decade of theoretical exercises. After 1998, it looked, suddenly, like a prophecy. Paul Steinhardt of Princeton and others took up the framework and pushed it in a variety of directions. Some models had the field slowly rolling downhill toward a lower energy. Some had it climbing. There were phantom energy models, in which the effective pressure was even more negative than the cosmological constant demanded, and in which the future ended not in a slow thinning but in a sudden tearing of every bound structure, galaxies, stars, atoms, a scenario given the memorable name of the Big Rip. There were tracker models in which the field naturally converged from a wide range of initial conditions on the value observed today. There were models in which dark energy interacted with dark matter. There were models in which it interacted with itself. For a few years, the theoretical landscape of dark energy looked like a garden that had been left untended for a long time and was suddenly, riotously, in bloom. And yet, in the end, the field did not choose the garden. The field chose lambda. Not because the alternatives were disproven, they were not, but because lambda was, at every measurement, sufficient. The supernova data fit it. The measurements of galaxy clustering fit it. The maps of the cosmic microwave background when they arrived fit it, and fit it strikingly well. Every additional parameter proposed by a quintessence model was, when the data were held up against it, unnecessary. Occam's razor cut in the direction of the constant. If a single number could explain the observations, why introduce a whole field with its own dynamics? Understand that this was a considered choice. It was not laziness. It was not the default. Physicists know how strange it is to accept that the vacuum has an energy of its own, and how much stranger the specific value of that energy is. When you try to calculate what the energy density of empty space ought to be, using the tools of quantum field theory, the answer that comes back is not a little different from what cosmology observes. It is different by roughly 120 orders of magnitude. That number is not a typo. It is the largest disagreement between theory and observation anywhere in physics. Choosing the cosmological constant as your model of dark energy means choosing, at the same time, to sit with that disagreement. It means signing up for the worst fine-tuning problem in the history of the discipline and hoping that some future insight will explain how a number so vast in principle came to be so small in practice. The community signed up anyway, because lambda worked, because every alternative was more complicated and none of them made the data fit better. Because in physics, when the plain answer is compatible with everything you can measure, the plain answer is where you camp until something forces you to move. And so, by the middle of the 2000s, lambda CDM had congealed into orthodoxy. 68% dark energy, treated as a cosmological constant, 27% cold dark matter, 5% ordinary matter, the atoms of stars and planets and bodies, what Lawrence Krauss once described, in a phrase that has stuck to the field like a burr, as a bit of pollution in the grand scheme of things. That was the recipe. That was the universe. And the dark energy in it, by the terms of the consensus, was fixed, unchanging. The same value at every point in space and the same value for all time. That was the decision. That was the shape of the ground on which the next quarter century of cosmology built. And to understand how much of a structure was raised on that ground, how many predictions, how many surveys, how many long careers, how many textbooks, how many quiet convictions about the ultimate fate of everything, we have to follow next the story of how the constant was cemented into place. Not by the supernovae alone, by the maps of an infant sky and by the missions that made them. The infant sky is a phrase worth pausing on before we go anywhere near a spacecraft. It refers to a moment in cosmic history that is, on the face of it, almost impossible to describe in ordinary language, about 380,000 years after the beginning, a duration that sounds long to a human and is essentially an eye blink to a universe. The hot plasma that filled all of space had cooled just enough that electrons could settle into orbit around nuclei and neutral atoms could form for the first time. Before that moment, light could not travel far. It was scattered again and again off free electrons, the way a headlight is scattered inside fog. After that moment, the fog cleared. Light was suddenly free to move in straight lines across an expanding cosmos. That light has been travelling ever since. It has been stretched along the way by the expansion of the space it moves through, so that by the time it arrives at us it is no longer visible, no longer even infrared, but microwave, a faint, cold, almost perfectly uniform bath of radiation coming from every direction at once. That bath is the cosmic microwave background. It is, in a real sense, a photograph of the universe as it was when it first became transparent. And every detail in that photograph, every faint ripple in its temperature, is a fossil of what the universe was doing in the moments before. To measure that photograph accurately is to measure the universe. And by the end of the 1990s, the community understood that the next great tests of lambda would come not from exploding stars in nearby galaxies, but from the pattern of hot and cold spots in that ancient light. The supernova results had opened the door. The microwave sky, mapped with sufficient precision, would tell you whether you had walked through the right door, so the community built the instruments to measure it. The first of the two great missions of this era carried a name that most people, even most curious people, would struggle to say aloud from memory. DESI, the Wilkinson Microwave Anisotropy Probe, named for a physicist who had spent much of his career on precisely this question, and who had died before the mission he had helped shape reached the sky. It launched from Cape Canaveral in the summer of 2001, on a Delta II rocket, on a warm afternoon in Florida, and it went not into orbit around Earth in the ordinary sense, but out to a point roughly 1 million miles beyond us, in the direction opposite the Sun. That point has a technical name, the second Sun-Earth Lagrange point, and a simpler description. It is a place where the gravitational pulls of Earth and Sun combine in such a way that a small spacecraft can, with only modest corrections, hold its position relative to both. It is quiet there. It is cold. It is far enough from Earth's warmth and radio noise that a telescope pointed away from the Sun sees, across almost the whole of its field, only the ancient microwave sky. WMAP would spend the next 9 years there, spinning slowly, sweeping the sky in overlapping arcs, measuring tiny differences in temperature between one patch of the microwave background and the next. The principal investigator for the mission was Charles Bennett, a physicist at Johns Hopkins with the kind of career that the general public rarely hears about, and that a field like cosmology depends on absolutely. Bennett is not a household name. He does not appear in popular anthologies of great scientists. He is a builder of instruments, a manager of teams, a person whose skill is the unglamorous one of coaxing an enormously complicated machine to deliver clean numbers year after year. His job, and the job of the several hundred people who worked with him, was to turn a photograph of the infant sky into a set of parameters. How old is the universe? How fast is it expanding? What is it made of? How much of it is ordinary matter? How much is cold dark matter? How much is that stranger thing, that lambda, that constant that Perlmutter and Schmidt and Rees had put back onto the equations 3 years before the launch. The answers, when they came slowly. WMAP released its results in stages, each release refining the last. The temperature map deepened, the uncertainties tightened, and the numbers that emerged did something that the community had been half expecting and half dreading. They agreed with the supernovae. They agreed with the model in which roughly 2/3 of the universe was dark energy, and roughly a quarter was cold, dark matter, and only a small remainder was the ordinary stuff of stars and planets. They agreed with a specific age for the universe, a little under 14 billion years, that has held up with small refinements ever since. Say that number slowly. Nearly 14 billion years since the light we are measuring first escaped its fog, and within the small uncertainties of the measurement, the dark energy in that model behaved, at every scale WMAP could probe, exactly as if it were a cosmological constant. Not a field slowly evolving, not a subtle drift, a constant. There is a particular kind of quietness that settles over a field when two independent lines of evidence, using entirely different methods on entirely different eras of the universe, deliver the same answer. The supernovae had measured relatively nearby exploding stars over the last several billion years. UMAP had measured a photograph taken 13.5 billion years earlier. These are not the same experiment repeated. These are not even the same kind of observation. And yet they were pointing at the same recipe for the cosmos, with the same fraction of dark energy in the mix, and the same behavior for that dark energy over time. Physicists, when this happens, tend to feel something they will not always admit to feeling. They feel that they have found something real. WMAP delivered its final results in the early 2010s, and by then it was already being succeeded. The European Space Agency had built its own microwave background mission, larger, more sensitive, more expensive, more ambitious. Its name was Planck, after the German physicist whose work on the spectrum of thermal radiation more than a century earlier had cracked open the door to quantum mechanics. Planck launched in the spring of 2009 on an Ariane 5 rocket from the equatorial spaceport of the European Space Agency in French Guiana. It travelled to the same distant, quiet place WMAP had gone, and it began to make its own map. If WMAP had produced a good photograph of the infant sky, Planck produced a great one. It measured more frequencies. It measured them with finer angular resolution. It measured them with lower noise. Where WMAP had teased out the largest features in the microwave background, the biggest patches of slightly warmer and slightly cooler light, Planck could resolve smaller and smaller ripples down to angular scales corresponding to the smallest primordial structures that would eventually collapse into galaxies. The team of scientists behind Planck was, in the manner of European megaprojects, sprawling. But a name that sits near the centre of the enterprise is George Efstathiou, a professor of astrophysics at Cambridge, one of the founders of the modern cold dark matter model of structure formation, a person who had spent decades of his life working out what a universe with the ingredients we now assume would actually look like. Efstathiou and his colleagues had, in a real sense, been rehearsing for Planck for their entire careers. Planck's results came out in a series of releases through the 2010s, and each release did the same thing WMAPs had done, only more so. The parameters tightened, the age of the universe, 13.8 billion years, give or take a small handful of tens of millions, became one of the best measured numbers in physics. The composition of the universe, in the framework of lambda CDM, was pinned down to a precision that would have seemed unimaginable a generation earlier, and once again dark energy behaved like a constant. Its equation of state parameter, that number the theorists had called W, the one that would be exactly -1 for a true cosmological constant and something else for anything more interesting, sat within the uncertainties on -1, not slightly off, not tantalizingly drifting, sitting on the value the simplest model predicted. Let me put that in perspective. 2 spacecraft, each parked at a point in space roughly 1 million miles from Earth, each staring at radiation whose photons had been travelling for nearly the entire history of everything, had between them measured the ingredients of the universe with a precision that any 19th century astronomer would have called impossible, and any 20th century astronomer would have called a fantasy. And what they had found, when the numbers were done, was that the model built from a handful of Type Ia supernovae in the late 1990s had been essentially correct. The pie chart of the cosmos was real: 68% dark energy, 27% dark matter, 5% atoms, and the dark energy, so far as the data could tell, was a constant. Around these two flagship missions, a whole architecture of other measurements had been rising in parallel. Ground-based telescopes had been measuring the way galaxies cluster on the sky, mapping the faint imprint of an ancient sound wave, the baryon acoustic oscillation, that had rippled through the early plasma and left its signature in the distribution of galaxies today. That imprint served as a kind of ruler laid down across cosmic history, a length whose true size the physics of the early universe fixed to high precision, and whose apparent size, measured at various distances, told you how the universe had expanded in between. The ruler agreed with lambda CDM. Other telescopes had been measuring the way distant galaxy shapes are subtly distorted by the gravity of dark matter along the line of sight, the technique called weak gravitational lensing, and mapping, from those distortions, how clumpy the universe is on the larger scales. The clumpiness, within its uncertainties, agreed with lambda CDM. A cascade of independent measurements taken on different instruments by different teams using different physics converged on the same recipe. Rest with that for a moment, because it explains why the mood in cosmology, by the middle of the 2010s, was not one of open crisis. It was, if anything, one of quiet triumph. Every place you looked, the model held. Every new dataset that came in tightened the same constraints, and in the corridors of the field, among the people who had built their careers on the harder questions, a strange new anxiety began to be spoken aloud. Not that cosmology had failed, that it had succeeded too well, that the great questions of the discipline had, by luck and effort and the slow perfection of instruments, been so thoroughly answered that there might be nothing significant left to discover. You would hear it in senior talks, softened as a kind of joke, but with a real edge underneath. What do we tell the graduate students? What do we point the next generation of telescopes at if the recipe is settled and the parameters are measured to 3 decimal places? The field had, in the deepest sense, feared its own completeness, and through all of it, running like a hairline crack through the base of the marble, was the problem that would not go away. The problem of what dark energy actually is. Because for all that lambda fit the data, for all that WMAP and Planck and the galaxy surveys had agreed on its numerical value, no one had produced a first principles explanation for why that value was what it was. The community had chosen the cosmological constant because it worked. It had not, in any deep sense, understood it. And the reason it had not understood it was, and remains, one of the strangest facts in physics. Empty space, according to quantum field theory, is not empty. It is a sea of fluctuating fields. Every kind of particle that exists has, associated with it, a field that permeates all of space, and every one of those fields is, at the smallest scales, humming with quantum fluctuations. Pairs of particles and antiparticles flicker into being and vanish again on timescales too short to interact with in the usual sense. This is not a metaphor. It is a description of the vacuum that has been tested, in indirect but conclusive ways, in the laboratory. The Casimir effect, a tiny but measurable force between 2 uncharged metal plates in a vacuum, is one of those tests. The plates are pushed together by the pressure of vacuum fluctuations on either side of them, and the size of that push is exactly what quantum field theory predicts. Vacuum energy is real. It has physical consequences. You can measure them. Now here is the difficulty. If you take the same theory that predicts the Casimir effect correctly, and you ask it to predict how much energy density the vacuum ought to have on average, how much it ought to weigh, in a sense, per cubic centimetre of otherwise empty space, the answer that comes back is enormous, vastly, absurdly enormous. It depends on where you cut off the calculation, but any reasonable cutoff gives you a number that's larger than what cosmology observes for the cosmological constant, by a factor of roughly 10 to the 120th. That is a 1 followed by 120 zeros. Let me try once more to give you a feel for it. If you piled up every atom in every star in every galaxy in the observable universe, you would have a number that is unimaginably vast, and yet it is a number that, written out in ordinary digits, would still fit on a single line of a book. 10 to the 120th is beyond that. It is the largest single mismatch between what theory predicts and what observation finds anywhere in physics. Nothing else in the discipline comes close, not by many, many orders of magnitude. This is the cosmological constant problem. It has 2 versions, sometimes called the old and the new. The old version asks why the vacuum energy is so absurdly small, when quantum field theory says it should be so absurdly large. The new version asks why, out of all the moments in cosmic history, dark energy has come to dominate the universe now. why its density is comparable to the density of matter in our particular era, when for almost all of the past it was negligible, and for almost all of the future it will be everything. Both versions of the problem are real. Both remain unsolved. Steven Weinberg was one of the physicists who framed the problem most clearly. Weinberg was one of the great theoretical minds of the second half of the 20th century, a Nobel laureate for his work on the unification of the electromagnetic and weak nuclear forces, a person whose textbooks generations of physicists have learned the field from. And in the late 1980s, working before the discovery of dark energy, before there was even a positive value of lambda to explain, only an upper limit, Weinberg wrote a paper that framed the puzzle in a way that has haunted the discipline ever since. He asked what a universe with a much larger vacuum energy would look like, and he pointed out that in such a universe, the accelerating expansion would have kicked in too early, tearing gas clouds apart before they could collapse into galaxies. No galaxies, no stars, no planets, no observers to notice. He suggested cautiously that the observed value of lambda might be selected by the fact that we are here to observe it, that only a universe with a very small cosmological constant could contain the kind of complexity that eventually asks questions about cosmological constants. This is the argument that goes by the name of anthropic reasoning, and it makes many physicists uneasy. It has the flavour of an explanation and the structure, some feel, of an evasion. It says nothing about why the vacuum energy has the specific value it does. It says only that if it had a very different value, no one would be here to complain. Leonard Susskind at Stanford, one of the founders of string theory, embraced the anthropic argument as a possible way through. In Suskind's picture, the equations of string theory admit a vast landscape of possible vacuum states, an inconceivable number of them, sometimes written as 10 to the 500th, an unimaginable number of possible universes, each with its own set of physical constants. And our universe is simply the one, or one of the ones, in which the constants happen to be compatible with our existence. This is the megaverse view. It is elegant in a certain unsettling way. It is also at present untestable. Not all physicists find that acceptable. Weinberg himself, until his death in 2021, spoke of the cosmological constant problem as something he hoped would find a better solution than anthropic selection. Others in the field have spent long careers looking for that solution, for some mechanism, some symmetry, some structure of physics that would explain, from first principles, why the vacuum weighs what it does. None of those searches has succeeded. The problem sits, unresolved, at the base of the Standard Model, 120 orders of magnitude unaccounted for, the largest embarrassment in physics, quietly present in every calculation the discipline performs. And this is the point that a listener needs to hold, because it will matter enormously when we come back, later, to what DESI has begun to see. Lambda CDM was the consensus not because lambda was understood. It was the consensus because lambda fit the data and nothing simpler did. The field had accepted into its most foundational model a number it could not derive from anything. It had built on top of that number a picture of cosmic history and a picture of cosmic fate. It had extrapolated that number outward, forward in time, tens and hundreds of billions of years into the future, and used it to predict the eventual cold, thin, dark end of everything. And through all of that construction, the number itself remained an empirical parameter, inserted by hand with no first principles explanation. This is a strange kind of ground to build on. It is not weak ground. It is ground that has held every measurement laid on it for a quarter of a century. But it is ground whose foundations have never been dug down to. Physicists who are professionally cautious about such things understood this all along. They said so in review articles and in colloquia, and in the introductions of the papers that reported new results. Lambda CDM, the field said, is a model, not a theory. It describes the universe we live in with remarkable precision, and it does not explain the most important thing in it. The most important thing in it, the 68%, the ingredient by mass energy that dominates all the others, is a parameter whose physical origin is unknown. That is the situation the community carried into the middle of the 2010s. Every measurement agreed. Every new mission tightened the numbers. The recipe of the universe was, by every observational standard the discipline could muster, well established. And beneath it, ignored in daily work but never truly forgotten, sat that enormous unexplained discrepancy, the cosmological constant problem, the theoretical wound, the reminder that the whole edifice was resting on a value the theorists could not derive and the observers could only measure. If, at that moment, someone had asked what could possibly disturb this consensus, most cosmologists would have answered honestly. They would have said that a truly new experiment, one that could measure how dark energy has behaved over billions of years of cosmic history with greater precision than anything before it, might eventually see a departure from lambda. Might. Probably would not. The bet in the community was on lambda. But the honest answer was that the question was open, that the constant had been assumed in a certain sense on trust, and that any experiment sensitive enough to test that assumption directly was worth building. And so, in the same years that Planck was polishing its final results and WMAP's data archive was being handed to the next generation, plans were being drawn up in a laboratory in the hills above San Francisco Bay for an instrument that would do exactly that. A machine designed from the metal of its frame outward to answer the one question the consensus had been unable to ask of itself. Not whether the universe was accelerating, that was settled, but whether the thing driving the acceleration was truly in the deepest sense a constant, or whether it had been changing all along, slowly, patiently, beneath the notice of every instrument that had come before. The machine that would ask that question was being built at Berkeley. Its home would be a mountain in the Sonoran Desert, and the telescope it would ride on had been staring at the sky, in one form or another, for half a century. The mountain is called Kitt Peak, and it rises out of the Sonoran Desert southwest of Tucson to a height of just under 7,000 feet. From the summit on a clear night, you can see the lights of the city 60 miles away as a faint glow along the eastern horizon, and above you, in every other direction, the sky opens into something a person who has grown up in a lit country has probably never seen. The Milky Way is not a smudge there. It is a river, banked with dust lanes and lit with individual stars arching from one horizon to the other. The air is thin, the nights are cold, even in summer, and on the highest ridge of the peak, inside a white dome that has stood there since 1973, is the telescope that would carry the instrument. The Nicholas U. Mail 4-meter telescope has been staring at the sky for half a century. It was, when it opened, one of the largest telescopes in the world. It has watched, through a succession of instruments bolted to its base and swapped out over the decades, the passage of a generation of astronomers and a generation of physics. It has been retrofitted, upgraded, refigured. The mirror is the same mirror, the mount is the same mount, but the eyes it looks through have changed with the questions being asked of it. And in the years leading up to 2020, engineers began removing its previous instrument and preparing its focal plane for something new. What arrived, from Berkeley, was a machine that at first glance resembled a piece of industrial jewellery, a hexagonal array of 10 wedge-shaped petals fitted together into a disc roughly the size of a manhole cover, each petal studded with 500 slender cylindrical robots. 5,000 robots in all, packed shoulder to shoulder, each one an independent little machine capable of pivoting its tip to a chosen point on the sky with a precision of about 10 micrometers, a tenth of the width of a human hair. Threaded into the tip of each robot was an optical fibre. The fibres ran, in careful bundles, out of the focal plane and down the side of the telescope and into a room below, where they terminated in a set of 10 spectrographs. Each spectrograph split the light delivered to it into its constituent wavelengths, and recorded that spectrum on a detector cooled almost to the temperature of dry ice. The choreography, once the survey began, was this. A control system, running in the observatory building through the afternoon, would consult a target list, a catalogue of galaxies and quasars pre-selected from earlier imaging surveys, and based on the current position of the sky, generate a plan. The plan specified for each of the 5,000 robots a small stretch of celestial coordinate where it should point. When the dome opened at dusk and the telescope swung to its first field, the robots would move quietly in unison. In something like a minute, each fibre tip was placed on its assigned galaxy. 20 minutes of exposure would follow. Then the robots would rearrange themselves for the next field. Then the next. In a good night, well over 100,000 galaxies would give up their spectra to the machine. Formal operations began in May 2021, after a 4-month trial run during which the collaboration collected 4 million spectra just to prove that the pipeline worked. Once the survey was underway, the pace was industrial. Every night, roughly 80 gigabytes of raw data flowed from Kitt Peak to a computing center in the Berkeley Hills, the National Energy Research Scientific Computing Center, a facility whose racks of processors hum in a room that has nothing to do with astronomy and everything to do with the sheer volume of numbers modern astronomy now produces. The pipeline would run overnight. By the following morning, calibrated spectra would be available to the collaboration, wavelengths corrected, sky background subtracted, flux calibrated, target classifications assigned, redshifts extracted. A cycle that, a generation earlier, might have taken a graduate student a year of careful work was now happening automatically every day for tens of thousands of galaxies at a time. None of this was easy. None of it was, in the phrase the field uses for such things, cheap. The calibration alone consumed years of work by dozens of people before the first cosmological number could be trusted. Sky subtraction, the removal of the faint background glow of the atmosphere from the spectrum of a distant dim galaxy, is a problem that gets harder the fainter the target. The Sonoran night sky is dark by any reasonable standard, but not perfectly dark, and its contribution to a raw spectrum can be many times larger than the signal of the galaxy itself. Every fibre, every wavelength, every exposure had to be understood well enough that the residual, after subtraction, was clean. Every optical element in the light path had to be characterized. The stability of the focal plane through a night's temperature changes, the response of the detectors as they aged, the tiny drift of the fibre tips over hours as the telescope tracked, the purity of the target selection, the fraction of objects the algorithm classified as galaxies at a given redshift that were, in fact, galaxies at that redshift. The collaboration held itself to a standard above 99% on that last measure, and the labour of getting there and staying there is one of the invisible triumphs of the whole enterprise. Andreu Font-Ribera, working out of the Institute for High Energy Physics in Barcelona, had by then spent much of his career on a particular subset of this problem: the use of the light of distant quasars as a probe of the intervening universe. Quasars are the most luminous objects in the cosmos, the accretion disks around supermassive black holes in the young centres of forming galaxies, and their light, on its way to us across billions of light-years, passes through vast intergalactic clouds of hydrogen. Each cloud absorbs a small line out of the quasar's spectrum, and by the time the light reaches Earth, those lines have been stretched and multiplied into a dense forest of absorption features, the Lyman alpha forest. From that forest, painstakingly, you can reconstruct the distribution of matter along the line of sight, at redshifts too high for ordinary galaxies to trace. Font-Ribera and his collaborators were the people who taught DESI how to read that forest. Nathalie Palanque-Delabrouille, one of the co-spokespeople of the collaboration during the years the survey was being built and brought online, had come out of that same tradition, the use of quasar spectra as cosmological probes, and had grown, by the middle of the survey, into one of the public voices of the project. She would later describe, in a phrase that captures the tone of the collaboration, as the first-year data came in, the astonishment of being able, with only that first year, to measure the expansion history of the universe at 7 different slices of cosmic time, each slice pinned down to a precision of between 1 and 3%. That is the sentence to sit with for a moment. 7 epochs, spanning 11 billion years, each one measured, from the ground to within a few parts in 100. The universe, in its rate of unfolding, was being sampled as if by a very careful hand taking readings from a very old clock. The clock, of course, was the baryon acoustic oscillation ruler, that fossilized sound wave from the first 400,000 years of cosmic history, frozen into the distribution of matter at a physical scale of about 150 megaparsecs, roughly 490 million light-years across. Wherever you look in the galaxy distribution, at whatever redshift, you find a slight preference for galaxies to sit at that separation from other galaxies. It is a subtle statistical bump in the count of pairs. It is not visible to the eye, it is not visible in any single patch of sky, but integrated over millions of galaxies, it emerges, the same bump, at the same physical scale, everywhere the survey looks. And because the bump has a known physical size, you can use its apparent angular size at a given redshift to measure how far away that redshift is. The universe's expansion history is written in that pattern. The whole reason DESI was built, the whole reason 5,000 robots were bolted onto a 50-year-old telescope in the Arizona desert, was to read that pattern with a fidelity nothing before it had achieved. By the end of the first year of survey operations, 6 million galaxies and quasars had been observed with high-confidence redshifts. By the time of the Data Release 1 announcement in March of 2025, That number would rise to more than 18 million objects, drawn from an even larger pool of 47 million galaxies and quasars and 20 million stars that the instrument had spectroscopically inspected. The scale of the map being built had no precedent. Every previous survey had been, in some sense, a rehearsal for this one, and the point of building it, the reason the collaboration had accepted the years of instrument work and calibration and pipeline development and target selection and blinded analysis, was not to see whether the universe was expanding. That was known. It was to see whether the thing driving the expansion was truly constant, or whether, hidden in the 7 slices of cosmic time, there was a shape to it, a drift, a change. By early 2024, the pipeline had processed the first year. The analysis teams had been working with blinded numbers, a deliberate procedure by which the final cosmological parameters were hidden from the researchers themselves, replaced by offsets and scramblings that let the pipeline be tested and refined without anyone being able to see which direction the answer was pointing. This is a discipline the field has learned, sometimes painfully, over decades. Human minds, even careful ones, are pattern finders. Show a researcher a preliminary number that agrees with expectation, and the researcher may, without knowing it, without intending it, stop looking for the last subtle bug in the code. Show a researcher a preliminary number that disagrees with expectation, and the researcher may find, without meaning to, an additional systematic to correct for. The only defense against this is not to know. To do the analysis entirely on numbers whose truth has been hidden, and only at the end, when every check has been run, every cross-check completed, every systematic accounted for, to unblind and see what the data actually said. The unblinding, when it came, was one of those moments the collaboration would afterwards find hard to describe. The room, for those who were in it. The screen, showing the plot. The parameter called W, the equation of state parameter of dark energy, which in the standard model of cosmology sits, and has always sat, at exactly -1. The number that says the dark energy is a cosmological constant, the number the whole edifice rested on. The plot did not show -1, or rather, it showed -1 as one possibility among many, sitting near the edge of a region the data preferred. The preferred region, the place the numbers actually pointed, was somewhere else, not by much, not by an enormous margin, but by enough to notice. The collaboration had, for this analysis, employed a parameterization first written down in the early 2000s by Michel Chevalier and David Pulaski, and used ever since as the standard way to describe a dark energy that might evolve. In that parameterization, W is not a single number but a pair, or naught, which is the value of the equation of state today, and WA, which describes how it has changed with the scale factor of the universe, that is, with cosmic time. If dark energy is a true cosmological constant, well, naught equals -1 and WA equals 0, exactly. Any other combination of values describes a dark energy that has behaved differently at different epochs. The theorists had spent a generation building families of models, quintessence fields and their cousins, that predicted various shapes for such an evolution. The DESI year 1 data, unblinded, preferred a W status naught slightly greater than -1 and a WA distinctly negative. Translated back into physics, a dark energy that, in the past, behaved more strongly, more like an aggressive push, and that has been, in the recent history of the universe, weakening, growing gentler, softening its foot on the accelerator. The significance of the deviation depended on what other datasets were folded in. DESI on its own had strong constraints, but the tightest results came from combining the baryon acoustic oscillation measurements with the cosmic microwave background from Planck and with modern Type Ia supernova samples. In the combination with certain supernova compilations, the departure from a constant reached values in the range of 2.5 sigma. In the combination with others, it climbed toward 3, and in one combination, past 3. A 3 sigma result, in the language of the field, means the observed data is inconsistent with the null hypothesis, in this case with a cosmological constant, at a level of roughly 1 part in 300. It is not a discovery. Physics has, for decades, held itself to the far stricter standard of 5 sigma before calling something discovered, 1 part in 3.5 million, a threshold set in reaction to a long history of promising signals that dissolved into nothing when scrutinized. A 2.5 or 3 sigma anomaly is, in that culture, a strong hint. It is a whisper the data is making. It is not yet the data speaking. But 3 sigma, in a place no one had firmly expected it, on the parameter that governed the fate of everything, was not a whisper the collaboration could ignore. They had built the machine to ask exactly this question. The machine had answered. The answer was not the one the standard model predicted. The mood in the room, and in the many rooms in many countries where members of the collaboration sat looking at the same plot on their own screens, has been described afterwards in different ways by different people. Excitement was the word that came up most, and it was almost always followed, in the same breath, by the word skepticism, or the word caution, or the phrase "we have seen this before." The field has, over decades, developed something like an immunological response to results at this level of significance. 3 sigma anomalies come and go. They appear, they are debated, they draw a wave of theoretical papers proposing new physics to explain them, and then they weaken, and then they vanish. The history of particle physics is littered with them. The history of cosmology has its share as well. Anyone who had been in the field for 20 years had watched at least one such signal rise and fall. Mustafa Ishak Bushaki, at the University of Texas at Dallas, was one of the co-chairs of the working group inside DESI, whose job was to interpret exactly this kind of result, and he was among the people whose responsibility it was, in the weeks between the unblinding and the public announcement, to press on the numbers from every side. Was there a systematic that had been missed? Was there a subtle correlation between measurements that had been assumed independent? Was the parameterization itself introducing a preference? Could a truly constant dark energy, seen through the lens of the W0, were form, sometimes look, under noise, like an evolving one? Every question of that kind that could be asked was asked. Every check that could be run was run. The signal held. That is not the same as saying the signal was real. The collaboration was and remained entirely careful on that point. What could be said at the end of the internal review was that the pipeline was behaving as designed, that the input data was clean to the standards that had been set, that the analysis choices were defensible, and that under those choices the data preferred an evolving dark energy over a constant one at somewhere between 2.5 and 3 plus sigma, depending on which external supernova sample was folded into the combination. Whether that preference reflected a real feature of the universe, or a statistical fluctuation, or an as yet unidentified systematic somewhere in one of the datasets, could not, from year 1 data alone, be determined. Michael Levier, the director of the project, put it, in the days around the public announcement, in the careful phrasing that has become characteristic of the collaboration's public voice. So far, he said, they were seeing basic agreement with the best model of the universe, but also some potentially interesting differences that could indicate that dark energy was evolving with time. Read that sentence closely. Basic agreement and interesting differences. The polite formulation of a result that had not yet chosen a side. A result that could, when the next year of data was added, dissolve back into consistency with a constant and be forgotten. Or that could sharpen and grow and become something else. On the 4th of April 2024, the collaboration released the papers. They went up on the Arxiv preprint server, dozens of them, thick with tables and figures and appendices detailing the calibration and the systematics and the statistical methods. The lead author list on the flagship cosmology paper ran to hundreds of names. The results were presented simultaneously at the American Physical Society meeting, and a press event was held at Berkeley to explain to the wider public what the collaboration had found. The word the press releases used carefully was hint. The dark energy might be evolving. The data pointed gently in that direction. There was more to come. Year 2 was already being collected. Year 3 would be added within a year. The picture would sharpen. And the picture, as would become clear in the months and then the year to follow, did sharpen. But that is the next chapter. What matters, in the room that April, was that a machine designed to ask a single question had returned an answer, and the answer was not the one that had been assumed for a quarter century. It was too early to say the answer was right. It was too early to say anything definitive. But the whisper the field had in its more speculative moments half expected, the whisper that lambda might not be quite lambda after all, had for the first time been heard clearly enough to raise the hair on the necks of the people listening. They had built on the mountain above the desert an instrument capable of hearing that whisper. They had spent years teaching it to listen. And on the night the pipeline finished and the plot appeared on the screen, what the instrument reported back was not silence, and not the flat, steady note of a constant, but a slow, subtle drift. a signal that the thing the field had assumed unchanging might, in fact, have been changing all along patiently, beneath the notice of every measurement that had come before. What that would mean, if the signal held, for the model, for the community that had built the model, for the fate the model predicted, was a question that would take the following year to begin to answer. But the question had, at last, been opened. The consensus, which had rested for 25 years on the assumption that dark energy was constant, would now have to sit with the possibility that it was not. And the people who had spent their careers building that consensus would have to decide, one by one, what to do with the whisper the machine had brought back. The reaction, when it came in waves. It came first from the small circle of people who had known the result was coming, the members of the collaboration itself, and the handful of colleagues at other institutions who had been briefed under embargo in the days before the papers went public. It came next, within hours of the archive posting, from the wider community of working cosmologists, the ones who had been waiting for exactly this kind of measurement, and knew precisely how to read the plots that were now spilling across their screens. And it came finally, over the following days and weeks, from the outer rings, the theorists whose careers had been shaped by the assumption of a constant lambda, the string theorists who had long argued that a constant lambda might not be theoretically permissible in the first place, the science writers who had to translate the phrase basic agreement and interesting differences into a headline, and the general public who had grown up being told in every popular account of cosmology that the universe would end in cold and darkness, and that the end was known. Each of these rings responded in its own register, and taken together, their responses gave the field for the first time in a long time the texture of a discipline that had been startled awake. The most closely watched voice in those first days was Adam Rees. He had been, in 1998, one of the young astronomers who had helped discover the very thing DESI was now measuring. He had spent the intervening quarter century watching his discovery ossify into consensus, and he had spent the last decade in particular pursuing a separate tension, the disagreement between local measurements of the Hubble constant and the value inferred from the cosmic microwave background, that had earned its own name in the literature and its own low-grade crisis in the field. He knew, better than almost anyone alive, what a real signal felt like when it first arrived. He also knew what it felt like when a promising signal quietly evaporated over the next 2 years of data. He had lived both. When he spoke carefully. He called the DESI result, in a phrase that circulated widely and would go on being quoted for months afterward, the most significant hint about the nature of dark energy in a quarter century. It was a striking sentence coming from him. It committed him to nothing definitive. It made no claim about which way the signal would go, but it placed the result, in the taxonomy of hints, at the top of the pile. In 25 years, he was saying, nothing else had come along that had this shape and this weight. That, from one of the co-discoverers of the accelerating universe, was as strong an endorsement as caution allowed, and caution from him was the point. He was careful, in the same interviews, to remind people of what he had watched over his career, the tantalizing shapes that had emerged from partial datasets and dissolved when the datasets grew. He was careful to note that a 3 sigma preference was not a discovery. He was careful to leave every door open. He was, in short, doing what a person who has been through this before does. He was allowing himself excitement and forbidding himself belief. Wendy Friedman spoke from a different angle. She had spent decades of her career on the Hubble constant, on the painstaking calibration of the local distance ladder, on the question of how fast the universe is expanding right now, in this era, in our own neighborhood. She knew, as intimately as anyone in the field, how many places a measurement can go quietly wrong. She knew how many assumptions ride silently on the calibration of a standard candle. And she knew that the interpretation of the DESI signal depended on the interplay of several datasets that did not, at this moment, all agree with each other. The Hubble tension, unresolved for years, sat in the background of every conversation about cosmology now. Friedman raised in her responses the possibility that this new tension and that older one might be entangled, that whatever was going on with the local expansion rate might be muddying the interpretation of what DESI was seeing, and that until that older tension was understood, the new one could not be cleanly read. It was not a rejection. It was not a dismissal. It was a reminder from someone who had spent a long career watching cosmology's supposed simplicities come apart under closer inspection, that a signal read in isolation is a signal read incompletely. The universe, she was quietly saying, is not obliged to make its mysteries independent of one another. If lambda CDM was in trouble, it might be in trouble in more than one way at once, and the trouble in one place might be shaping what we saw in another. Until we knew, we would not know. And then there was Kumran Vafa. He worked in a different building of the discipline. He was a theorist, a string theorist at Harvard, who had spent years arguing from within the mathematics of string theory itself that the universe we appear to be living in might, in a deep sense, not be a universe that string theory allows. The argument had a name. He called it the swampland, the set of effective theories that look at low energies, like our world, but that cannot be derived from any consistent theory of quantum gravity. Those theories, Vafa argued, live in the swampland, and the mathematics of string theory forbids them. And among the conjectures that had come out of this program over the years was a striking one about dark energy, a true cosmological constant, an eternally unchanging vacuum energy that persists forever at the value we appear to observe, that some versions of the swampland argument held was not permitted. It could not be built. It could not sit stably in a fully quantum gravitational universe. Whatever was driving the acceleration we saw, therefore, could not, in this view, be constant. It had to be evolving. It had to be, in the language of the field, dynamical. For years, this had been a minority position among theorists and a curiosity among observers. It was the kind of prediction that most observational cosmologists filed away with a shrug. Interesting if true, unfalsifiable in practice, safely ignored. And now, from a mountain in Arizona, a 5,000 fiber instrument had returned a result that pointed gently in exactly the direction the swampland arguments had predicted. Vafa and his collaborators spoke, in the days after the announcement, with the measured pleasure of theorists who have been waiting a long time for the observational world to catch up. They did not overclaim. The signal was not yet a discovery, but it was the first data any of them had ever seen that was consistent, in a non-trivial way, with a prediction their program had been making for years. If the signal held and grew, the swampland would move, in the eyes of the field, from a mathematical curiosity to a serious contender for how the universe actually works. And a body of theoretical structure that had lived on the edge of the discipline would move, quietly, toward its centre. These were three voices. They were, in a sense, three sides of the same conversation. Rees held the middle, a discoverer's cautious hope. Friedman held the observational skepticism, the reminder that measurements entangle. Vafa held the theoretical stake, the position, held long before the data arrived, that the data now seemed faintly to support. And around them, across the community, hundreds of other voices spoke in every register between and beyond. There were those who suspected the result was a systematic buried somewhere in the calibration of the supernova compilations that had been folded in with the DESI data, a subtle bias in how the light curves of distant supernovae had been fitted, or in how the various samples had been stitched together. There were those who suspected the result was real and would grow, and who began, quietly, drafting theoretical papers to be ready when it did. There were those who suspected it was noise and who said so, and who were prepared to be right or wrong as the next dataset arrived. There were those who, having spent their careers on lambda CDM, said nothing at all and waited. What the whole community shared, in those first weeks, was a texture that had not been present in cosmology for a long time. Not certainty, not consensus, not the sense that had settled over the field in the years after Planck, that the map was drawn and only the details remained. Something older and more familiar to the discipline, and something that had, in the wake of the great successes of the 1990s and 2000s, gone slightly quiet. The texture of not knowing, the texture of a result on the table that could go either way, and of an argument in which no one at that moment could claim to be sure. Let that settle for a moment. For 25 years, the standard model of cosmology had been the object of a slow, steady tightening. Each new dataset had confirmed it. Each new probe had returned parameters consistent with the last. The community had, in its more honest conversations, admitted that this steadiness was itself a puzzle, that a truly correct theory tends to develop cracks as the precision improves, and that the total absence of cracks in lambda CDM was, if anything, suspicious. But suspicion is not a signal, and in the absence of a signal, the model had continued to stand. Now, for the first time, there was something on the table that was not a confirmation, not a definitive falsification either. Nothing had been ruled out at 5 sigma, nothing had been overturned, but something in the middle. Something that, if it held, would mean that the model as written was incomplete, and that the piece that was missing was precisely the piece the model had been built around. Dark energy, the largest single ingredient in the universe by the incounting of lambda CDM, might not be what the model said it was, and the fate that the model predicted, the long thinning, the slow cooling, the eternal descent into diffuse cold, might not be the fate at all. This is worth pausing on because it is the point at which the physics stops being an inside conversation and starts to be a conversation about the world. If dark energy is a constant, the future is known. It is not a comfortable future, a universe that grows steadily emptier, in which galaxies drift beyond one another's horizons, in which star formation eventually ceases and the last stars burn out, and the great slow processes of black hole evaporation carry the remaining structure away over spans of time that dwarf the current age of the universe by factors that written out in full would fill the width of a page. But it is known. It has a shape. The community had, over the past 25 years, quietly adjusted to that shape, the way a person adjusts to a diagnosis. It was cold, and it was long, and it was ours. If dark energy is not a constant, if the DESI signal held and grew and eventually crossed into discovery, then that diagnosis dissolved, not into a better one, into an open question, into a branching set of possibilities, each of which had its own physics, its own timescale, its own texture of ending, and none of which, at this moment, could be chosen among. Catherine Fries, at the University of Texas, had spent parts of her career on exactly those alternatives. She had worked on dynamic dark energy models, on scenarios in which the vacuum could shift, on cosmologies in which the acceleration was not the last word. In the wake of the DESI results she and others walked through, in interviews and in seminars and in the working papers that began to appear in the weeks that followed, what a weakening dark energy would actually mean for the future of everything. Consider the softest of the possibilities. Dark energy is weakening, as the DESI contours suggest, and continues to weaken, gradually, over the coming tens of billions of years. In this scenario, the cosmic acceleration slows. The universe still expands. The expansion, once begun, has enormous momentum, but the pressure driving the acceleration eases, and eventually, at some point in the deep future, the expansion becomes decelerating again. Gravity begins slowly to reassert itself. The distant galaxies, which under a constant lambda would have drifted beyond our horizon forever, might in this scenario remain, in principle, reachable. The long isolation of the big freeze is, at minimum, softened. The universe does not thin quite so relentlessly. It coasts, and then it slows. Consider a stronger version. Dark energy weakens further. It reaches zero. It crosses zero and becomes, in effect, attractive rather than repulsive. Gravity takes over. The expansion, which has been running for nearly 14 billion years, first slows and then halts, and then reverses. The galaxies, which have been separating, begin to approach. The universe contracts. Over spans of time that dwarf its current age, everything falls together. The cosmic microwave background, cooled now by the long expansion, warms again under compression. The night sky brightens, the temperature climbs, structures come apart, and at the end, in a mirror image of the beginning, everything converges toward a final singularity. A big crunch. The universe ending as it began, in a state of infinite density, out of which, some speculative models allow, a new expansion might begin. Consider then the stranger direction. Dark energy does not weaken toward zero. It shifts, subtly, in the opposite direction. Its density grows rather than shrinks. This is the phantom regime, a scenario in which the equation of state crosses a divide that classical lambda cannot cross. In the phantom regime, the acceleration does not ease, it intensifies. The expansion runs faster and faster. First, the larger structures are torn apart. Clusters of galaxies unbind, then galaxies themselves, then, on a shorter timescale, solar systems, then stars, then planets, and finally, in the last fraction of a second before the horizon collapses, atoms themselves are pulled apart, their nuclei and electrons carried away from each other by an expansion that has, at last, overcome even the strong force. A big rip. A universe ending not in cold or in fire, but in a violent, accelerating tearing that finishes, in some models, in a finite time, tens of billions of years hence, in scenarios that fit the shape of the DESI data at its edges. 3 futures, a softened freeze, a crunch, a rip, and the DESI signal at 3 sigma and change could not yet distinguish among them. It could only say, and even this it could only whisper, that the flat, unchanging lambda, which had implied one specific future among all possible futures, was, in the light of this data, no longer the best fit. Priyamvada Natarajan, at Yale, whose work sits at the intersection of gravitational lensing and the mapping of dark matter, framed the situation in the language of cosmic architecture. The universe we see, the arrangement of galaxies, the filaments of the cosmic web, the great voids between, is the product of a long argument between gravity and expansion. Dark matter clumps, dark energy stretches. The structures we observe are the record of that argument at every epoch. What the DESI data appeared to be showing, faintly, was that the argument had not been steady, that the stretching had, over the 11 billion years the survey could see, changed its character. And if the character had changed in the past, there was no principled reason to assume it would not change in the future. The universe we lived in might not be the universe our great-grandchildren's telescopes would see. The fate of everything might not be a fixed destination that could be predicted from present measurements. It might be, instead, a trajectory that was still being written. That was the intellectual weather in the months after the April 2024 announcement. Hope in one direction, caution in another, vindication in a third, and beneath all of them, a shared awareness that the situation would not remain suspended for long. Year 2 of DESI's observations had been running in parallel throughout the analysis of Year 1. By the time the April announcement was made, the mountain was already halfway through gathering the data that would test the whisper. The pipeline that had produced the first result was being sharpened for the second. The systematic checks that had passed once would be run again, on twice the data. And the same collaboration that had, in April 2024, said hint, was preparing itself to say, one way or the other, something more definite the following spring. That spring came. The collaboration reassembled around the same instrument, the same mountain, the same procedure, with more than double the sample. Where Year 1 had produced roughly 6 million spectra, the second data release drew on approximately 14.25 million galaxy and quasar spectra. 3 years of observation, folded together, calibrated, blinded, analysed, unblinded. The papers were released on the 18th and 19th of March 2025. The flagship BAO measurements, the Lyman alpha forest analysis, the combined cosmological constraints. The results were presented formally at the American Physical Society's Global Physics Summit in Anaheim, California on the 19th of March. And the numbers this time were harder to look away from. The BAO measurements themselves, taken alone, remained broadly consistent with lambda CDM. That was true in Year 1, and it remained true in Year 2, and it will likely remain true in Year 5. The signal was not living in the BAO alone, it was living in the combination, in the joint fit of DESI's clustering data with the cosmic microwave background from Planck, and with the supernova compilations from the various collaborations that had inherited the 1998 result and extended it. Pantheon Plus, Union 3, DESY5. When those datasets were folded together, and the equation of state was allowed to vary, allowed, that is, to be described by the 2-parameter W0 waveform that captures a dark energy which changes with time, the preferred region of parameter space moved further from the point that lambda occupied. Not marginally, substantially. Depending on which supernova sample was chosen, the significance ranged from something in the neighbourhood of 2.8 sigma up to something in the neighbourhood of 4.2 sigma. The centre of that range sat past 3, and 3, in the practice of the field, is the threshold at which a signal stops being something that a physicist can honestly file under fluctuation, and starts being something a physicist has to file under phenomenon. Pauline Zarouk, a researcher at the Elpency in Paris and a member of the clustering analysis effort, was among those who described the atmosphere in the collaboration as the results came together. There is a specific quality to the moment when a blinded analysis unblinds and the plot resolves on the screen. The team knows what a null result would look like. They know what the previous year's result looked like. They have, in the abstract, considered every possible outcome. And still, in the instant the plot appears, there is a small breath of surprise, because the plot is not an abstraction. It is the answer. And the answer, that March, was that the contours had not softened. They had sharpened. The point lambda occupies sat further outside the preferred region than it had a year earlier. The whisper had not faded. It had risen, Not to a shout, not yet, but to something with the persistence and the shape of a real signal. Inside the collaboration, the mood shifted. It was not celebration. The 5 sigma threshold, the gold standard of the field, the value at which a result is formally acknowledged as a discovery, had not been crossed. There remained, and remains still, room for the signal to fade, or to shift, or to resolve into a systematic that no one has yet identified. The people who had built DESI knew this. They said it, publicly, in every interview and in every seminar. But the tone was different from the year before. In April 2024, the word had been hint. In March 2025, the collaboration allowed itself a slightly firmer register. Growing evidence, mounting preference, persistent signal. The language of a result that had survived its first serious test, and that would now, over the coming years, either continue to grow or reveal itself to have been a very sophisticated mirage. And around the collaboration, the wider community began to reorient. The theorists who had drafted preliminary papers in April 2024 published them in earnest in the spring of 2025. The swampland community, which had watched Year 1 with restrained interest, watched Year 2 with a different quality of attention. The observational teams that had counselled patients began, quietly, to redesign their own upcoming surveys with an eye to the parameter space that DESI was now excavating. And the theorists who had spent their careers on Lambda began the slow, uncomfortable work of asking themselves what a world without Lambda would look like, and what parts of the model they had built on it would still stand if the ground beneath it moved. Because a 3 sigma result held for a year and grown rather than faded is not a discovery. But it is, in the practice of the field, the point at which the honest question is no longer whether the anomaly is real. It is what the community is prepared to do if it is, and that question, once it is asked seriously, cannot be unasked. It moves through a field the way weather moves through a valley, slowly at first, then everywhere at once. By the middle of 2025, at conferences in Europe and North America, in seminar rooms at Princeton and Cambridge and Paris and Tokyo, the same conversation was happening in different accents. Not the loud conversation, the quiet one, the one that begins after the formal talk has ended and the coffee has gone cold and 2 people who have known each other for 30 years find themselves standing by a window, looking out at nothing in particular, saying the thing neither of them wanted to say first. What if we were wrong? Not wrong in the sense that the model failed. The model has not failed. Lambda CDM still fits the cosmic microwave background, with a precision that borders on the uncanny. It still predicts the observed clustering of galaxies across enormous swathes of the sky. It still recovers, to within its stated uncertainties, most of what the field has measured for a quarter of a century. A theory does not survive 25 years of increasingly punishing test by being wrong in any simple way. What the DESI results suggest, if they hold, is something more delicate and more painful. Not that the model was wrong, but that it was incomplete. That the piece at its centre, the piece labelled Lambda, the piece that carries 68% of everything and dictates the ending of everything, was a placeholder all along, a symbol standing in for a physics no one had yet written down, a number that worked, and that was allowed to stand because it worked, and that was never quite understood by anyone who used it. This is the reckoning, and it is being conducted largely in a register the public rarely sees, not press conferences, not headlines, long emails between collaborators, notebooks filled with alternative parameterizations, Slack channels where someone at 3 a.m. posts a plot and asks whether anyone else can see what they think they see. Reanalyses of Planck data with priors adjusted to permit an evolving equation of state. Reanalyses of the supernova samples with different systematic treatments. Reanalyses of the weak lensing surveys, KIDS and DES and the early releases from Euclid, checking whether the tension DESI has surfaced also lives faintly in datasets no one had previously thought to interrogate that way. The field is, in effect, auditing its own foundations, patiently, line by line, without anyone quite saying out loud that this is what they are doing. The members of the Planck team, whose measurement of the cosmic microwave background remains the single most exquisite dataset in the history of cosmology, occupy a particular position in this reckoning. Their result, taken alone, is entirely consistent with a cosmological constant. The tension with DESI arises only when the 2 datasets are combined and asked to describe the same universe with the same parameters. And so the question, for the Planck community, has become whether the tension lives in DESI or in Planck, or in the assumption that the 2 experiments are measuring the same thing in the same way. George F. Stathiou, who has spent decades at the heart of the Planck analysis, has been among those who counselled that the community wait, that the DESI signal remain, for now, a preference rather than a conclusion, that the extraordinary claim receive the extraordinary scrutiny it deserves. This is not resistance, this is discipline. It is what a field does when it has learned, painfully over generations, that the universe is a patient teacher of humility, and that the most beautiful signals are sometimes the ones that turn out to be artifacts of the instrument that measured them. The supernova cosmology community occupies its own position in the reckoning. These are the people whose 1998 result founded the entire enterprise of dark energy, the people for whom the cosmological constant was not an inheritance but a discovery. Adam Rees, having called the DESI hint the most significant in a quarter century, has continued to hold the position of a scientist who has been surprised by data before, and knows what that experience feels like. Saul Perlmutter, speaking in the measured cadence that has characterized his public statements for 30 years, has framed the situation as the sort of moment the field prepared itself for from the beginning, the moment when the placeholder is either confirmed or replaced, and either outcome is a form of progress. Brian Schmidt from the Mountain in Australia, where the High Z team once developed the observational techniques that made the 1998 result possible, has spoken of the strange satisfaction of watching a younger generation dismantle, carefully, the model his own generation built. None of them has claimed vindication. None of them has claimed error. All of them have said, in essentially the same words, that this is what science is supposed to look like when it is working properly, which is another way of saying that this is what it feels like when the ground moves under a career. And within DESI itself, the skeptics, the members of the collaboration who from the beginning have argued for the strictest possible interpretation of the data, who have pressed hardest on the systematics, who have insisted that every alternative explanation be exhausted before the exotic one is considered, those voices have not gone silent. If anything, they have grown more visible. Because a healthy collaboration does not silence its skeptics when a signal grows. It amplifies them. It hands them the microphone. It asks them, publicly, to say what they think the result cannot yet be trusted to mean. Mustafa Ishak Bushaki, at the University of Texas at Dallas, who co-chairs the working group tasked with interpreting the survey's cosmological implications, has been among those who framed the DESI results with a scrupulous attention to what the data do and do not permit one to say. Ofer Lahav, at University College London, a member of the DESI Executive Committee whose career has spanned nearly every major cosmological survey of the last 30 years, has spoken of the responsibility a collaboration bears when its results carry the potential to overturn a consensus, the obligation in effect to be its own harshest critic before the field is asked to become one. This is the culture that a quarter century of Lambda CDM has built. A culture that has learned to trust its own model without worshipping it. A culture that has learned to publish its anomalies without inflating them. A culture whose leaders, when handed a result that could rewrite the ending of the universe, do not race to the microphones. They race to the systematics. They race to the alternative parameterizations. They race to the Planck likelihood chains and the supernova compilations and the weak lensing shear maps, looking for the mundane explanation that would let them, in good conscience, put the exotic one back on the shelf. And they have not yet found it. That is the shape of the reckoning, not a dramatic overturning, not a press release announcing the death of the standard model, a slow, patient, collective failure to make the anomaly go away. Every reanalysis that leaves the signal intact is another small vote against the mundane explanation. Every independent probe that surfaces even a faint echo of the same tension is another small weight on the same side of the scale. The scale has not tipped, it may not tip, but it has begun perceptibly to lean. And a field that has spent 25 years in a stable configuration is learning in real time what it feels like to stand on a floor that is no longer perfectly level. If the signal holds, and that remains the conditional on which everything rests, then Lambda will have to be abandoned a second time. Einstein's blunder, revived in 1998 to save the accelerating universe, will have served for exactly the length of one scientific generation before being retired again. And that retirement will not be the failure of the model, it will be its completion, because a placeholder that is finally replaced by a physics has done its job. The letter lambda will not vanish from the textbooks, it will be reframed. It will become, in the historical chapters, the symbol that carried the field for a quarter century while the instruments and the techniques and the surveys were built that would finally allow the field to see past it. It will be honoured in the way that scientific ideas are honoured when they are superseded, not as errors, but as necessary steps, without which the next step would have been unreachable. What replaces it, no one yet knows. The parameterizations the DESI team has used, the W0 and WA description that lets the equation of state slide from one value at early times to another value now, are themselves placeholders. They are ways of asking the data whether lambda is enough, not descriptions of what stands behind the answer. If lambda is not enough, then somewhere behind the numbers there is a field, a dynamical thing, a quintessence of some kind, or a modification of gravity on the larger scales, or a signature of physics that lives in a regime, the vacuum, the deep quantum structure of space-time, where the field has never yet had experimental purchase. Qumran Vafa and the Swampland community will point, with restrained satisfaction, to the conjectures they published years ago, suggesting that a strict cosmological constant may be incompatible with a consistent theory of quantum gravity. The quintessence theorists, whose ideas Ratra and Peebles first sketched in 1988, and Steinhardt developed through the following decades, will find their work move from the margins of the field back toward its centre. The modified gravity community, long treated as a somewhat eccentric cousin of mainstream cosmology, will find its parameter space suddenly the subject of serious observational attention. And through all of this, the older question, the cosmological constant problem, the embarrassing skeleton in Lambda CDM's closet, the 120 orders of magnitude between what quantum field theory predicts the vacuum should weigh and what cosmology measures it to weigh, will not be solved. It will simply be transformed. The problem will no longer be to explain why a constant takes a value it should not take. It will be to explain why a field evolves the way it does. The mystery will move. It will not shrink. That is the honest end of the story, at the moment this documentary is being written. Not a resolution, not a revolution, a hinge, a place at which the field turned its head and began, for the first time in 25 years, to seriously consider the possibility that the ending it had been telling itself was not the ending after all. What comes next, in strictly instrumental terms, is more data. DESI is not finished. Its primary 5-year survey concluded in April 2026, having mapped tens of millions of galaxies and quasars, and the collaboration is continuing observations through 2028 to extend and deepen the map. Each additional year of data narrows the contours, tightens the constraints, moves the significance up or down. If the signal is real, and if the trend of the first 2 data releases continues, then somewhere in the accumulating years the 3 sigma preference will become 4, and 4 will become 5, and 5 will become the moment at which the field formally acknowledges that lambda has been replaced. If the signal is a systematic, a subtle error in the modelling of galaxy bias, or in the treatment of the Lyman alpha forest, or in some assumption buried 3 layers deep in the analysis pipeline, then somewhere in the same accumulating years it will begin to fade, and the collaboration will trace the fade to its source, and the community will exhale, and lambda will stand. Neither outcome is guaranteed. Both remain, on the current evidence, entirely possible. That is what a 3 sigma result means. That is what the honest practice of the discipline looks like at this stage, and DESI will not be alone. Above the atmosphere, at the second Sun-Earth Lagrange point, some 1.5 million kilometers from the Earth in the anti-solar direction, the Euclid Space Telescope has been at work since its launch on a Falcon 9 in July 2023. Euclid is doing a different kind of measurement, a wide survey of the geometry of the dark universe through weak gravitational lensing and galaxy clustering, over a 6-year nominal mission that will map a substantial fraction of the extragalactic sky. Its systematics are almost entirely independent of DESI's. Its instruments are different. Its team is different. Its cross-check with DESI will be, in the coming years, one of the most closely watched comparisons in the field. If Euclid sees, in its own data, the same faint preference for an evolving dark energy, the 2 experiments together will build the kind of independent corroboration that a single dataset, however large, can never provide on its own. If Euclid sees a universe entirely consistent with a cosmological constant, the field will have to reckon with a tension between 2 of its most sophisticated instruments and go looking for the reason why they disagree. Further out, in the planning documents and the community white papers and the working groups that shape the next generation of experiments, a Stage 5 concept has been under discussion, an instrument sometimes called Megamapper, a proposed 6.5-meter telescope equipped with tens of thousands of fibers, designed to reach redshifts DESI cannot reach, to map the universe at epochs when dark energy's influence was smaller, but its evolution, if it evolves, was already underway. Such an instrument, if built, would not report its first results for the better part of a decade. But its very existence in the community's planning tells you something about how seriously the field is taking the possibility that DESI is right. You do not design a next-generation experiment to measure a parameter unless you believe that parameter is worth measuring more precisely than anyone has ever measured it before. And so the picture that emerges at the end of this account is not of a mystery solved. It is of a mystery honestly held. A field that has been told by its own instruments that the story it had been telling for a quarter century may need to be told differently, and that has responded not with denial and not with panic, but with the slow, methodical, sometimes painful work of asking the universe again and more carefully what it actually is. There is a lesson in that, not a lesson the field would state in those terms. The practicing scientists mostly resist that kind of framing. But the lesson is there, and it is worth stating plainly at the close. The universe does not owe us a static answer. It does not owe us a beautiful model. It does not owe us an ending we can accept. What we have, as a species with the instruments and mathematics and a stubborn desire to understand the largest thing there is a method. A slow, imperfect, self-correcting method for asking the universe questions and listening to its answers. Sometimes the answers confirm what we already believed. Sometimes they surprise us. Sometimes, as now, they suggest that a piece of the picture we thought was settled was only ever the best guess we had at the time, and that a better guess is beginning, faintly, to come into focus. The willingness to hear that, the willingness of a field to hold a 3 sigma preference open for years, to audit its own foundations, to invite its skeptics to the microphone, to say publicly that its most beloved model may not be the last word. This is not a weakness of cosmology. It is its greatest strength. A discipline that refuses to revise its beautiful theories is not a science. It is a devotion. The people who built Lambda CDM and the people who are now, if the data hold, preparing to move beyond it, are practicing the same discipline in both eras. They believed the model when the evidence supported it. They will let it go when the evidence requires it. That continuity of practice across a generation, across the discovery of dark energy, and the possible reformulation of dark energy, is the deepest thing cosmology has to offer. And the fate of everything, the question with which this whole account began, the question of whether the universe ends in a cold and eternal thinning, or in something gentler or something stranger, or something we do not yet have the vocabulary for, remains, at this hour, genuinely open. Not open in the sense that we know nothing. We know a great deal. We know the universe is expanding. We know the expansion is accelerating. We know that whatever is driving the acceleration accounts for the majority of the energy budget of everything. What we no longer know, with the certainty we thought we had, is whether that driver is constant, whether it will drive the expansion forever at ever-increasing rates until every distant galaxy has passed beyond the horizon and every star has burned out and every black hole has evaporated into the featureless warmth of a maximally entropic void, or whether it is a field weakening as the universe ages, in which case the acceleration itself will slow and the ending will be different, and the shape of the far future will have to be redrawn. Neither picture is comforting in any simple way. Both are vast beyond any human measure of vastness. Both contain, at their far edges, timescales that reduce every human life and every human civilization and every human concern to a rounding error on a number so large it cannot be spoken. But there is something in the fact of the question being open that is different from either answer being closed. There is a kind of dignity to a universe that has not yet finished telling us what it is. There is a kind of dignity to a species that has built the instruments to ask, and that has learned to accept whatever answer the instruments return. The night sky, on any clear evening above Kitt Peak or above your own city or above whatever place you happen to be, is the same sky it was in 1917 when Einstein wrote lambda into his equations to hold the universe still. It is the same sky it was in 1929 when Hubble showed that the universe was not still. It is the same sky it was in 1998 when the supernova teams announced that the expansion was accelerating, and the same sky it was in April 2024 when DESI's contours slid off the point that lambda occupied, and the same sky it will be in whatever year the answer, whichever answer it turns out to be, finally arrives at the 5 sigma threshold and enters the textbooks as settled physics. The sky does not change. The story we tell about the sky changes. And the honesty of the telling, the willingness to change the story when the sky patiently insists, is the thing worth carrying away from all of this. The instruments will keep looking, the collaborations will keep counting photons and fitting curves and unblinding analyses, the theorists will keep drafting alternatives, the universe will keep expanding at whatever rate it is actually expanding at, indifferent to whether we have yet worked out which parameter describes it best. And somewhere, on a mountain in Arizona, on a clear night, 5,000 small robots will hold 5,000 fibers in place with a precision finer than a human hair, gathering the light of galaxies that emitted that light before the Earth existed, and turning that light into numbers, and turning those numbers into a picture of what the largest thing there is doing, and has been doing, and will do. We do not yet know how the story ends. That is the honest ending. That is the ending the evidence at this hour permits. And there is a quiet grace in it, in the fact that after everything, after Einstein and Hubble and Perlmutter and Rees and Schmidt and Planck and WMAP and the 25 years of consensus and the 2 years of anomaly, the universe still has one more thing to say before it is done. We are, all of us, waiting to hear it.